integral calculus is in textbook section 1.3. So if differential calculus didn't scare you, then you will make new friends with integral calculus as well. So for differential calculus, we have 4 major concepts. They all come from the basic tool of del operator, where we'll apply this to a scalar dot product with a vector, cross product with a vector. We get gradient, divergence, and curl. So accordingly, for integral calculus, we will also have a basic tool, and then we'll apply this to a gradient, divergence, and curl. So the basic tool for integral calculus is fundamental theorem of calculus. So how does this look like? So we have line integral from a to b, capital F x dx equals fb minus fa, where fx equals df dx. So the integral of the derivative is given by the value of the function at the endpoints. So basically, this tells us how to integrate the derivative. And then we get the original function where the differentiation disappears. So the derivative can be replaced by gradient, divergence, and curl. So this would be really helpful for electrical field, magnetic field, when we replace the derivative by gradient, divergence, and curl. So let's look at first of all the fundamental theorem for gradient. So we replace this derivative by gradient. What we get would be from a to b, gradient infinite decimal path equals tb minus ta, where infinite decimal path equals to dx, x direction, dy, y direction, dz, z direction. So line integral of gradient is given by the value of the function at the endpoint. So here, t is a scalar function, and then gradient gives us a vector, so we have dot product here. And then this is infinite decimal path. We'll look at an example in a minute. First of all, I want to highlight here that this theorem for gradient gives us 2 properties. So first of all, because of this theorem, it becomes obvious that this integral is independent of paths. In the end, we only care about the endpoints. And then the second thing is, if we take a closed line integral on gradient, we will get 0 because the beginning point and end point, they are the same, so we get 0. Let's look at an example for fundamental theorem for gradient. This is example 1.9 of the textbook. So basically, we have 2 points. A is 0, 0, 0, and the coordinate of B is 2, 1, 0. So we have the scalar function t equals xy squared. So now, what is the line integral of the gradient from a to b? So if we directly apply a fundamental theorem for gradient, this becomes really easy. So basically, line integral from a to b, gradient, and then the infinite decimal vector along the path. This equals to TB minus TA. So TB, we have x equals 2, y equals 1. So here it gives us 2. And then TA, they're all 0. So TA equals 0. So we have 2. So this is really, really easy. So let's also use this opportunity to practice, to have a practice on a line integral. So let's extend this integral function. So if we want to calculate this without the fundamental theorem of gradient, first of all, we need to calculate the gradient itself. So we have gradient equals to x direction dt dx, and then y direction dt dy, and then z direction dt dz. So dt dx give us y square. Sorry, make a mistake. So here this equals to dt dx give us y square on the x direction, and then dt dy give us 2xy on the y direction. dt dz, there's no variable z here, so that's just 0. So this is a gradient. So we have many ways of doing this line integral. So one way is we take this path 1, and then we take this path 2, we arrive B. So from A to B, like this. Alternatively, we can directly take the straight line. This is path 3. So I'm going to just do this in the video, but you can follow the textbook and do another path as well. And to confirm that, fundamental theorem for gradient really is independent of path. So if you do integral along this path or integral along this path, you'll get the same result. So for this path, the direct path, we have this relationship between x and y, which is y equals half of x. You can see from the finishing point and all the points along the line, this is always valid. So we put this into this gradient function. What we get would be x squared divided by 4 on the x direction, and then let me check, x squared y direction, right? Yes. So that's a gradient. And then another thing we need to calculate is infinite decimal vector along the path. So we have dl equals dx, x direction, dy, y direction, and then dz, z direction. So when we do integral along the path, we also have relationship between dy and dx. They are corresponding to each other because they are along the same line. So dy equals dx divided by 2. So if we put this into this infinite decimal vector, we have dx on the x direction, and then half of dx on the y direction, and then dz. Actually, for the whole path, z equals 0. So actually here, z equals 0. That's why here is 0, and here will be 0 as well. Okay, so now we are ready to do the integral. So we have integral from A to B. So this, this one dot this one what we get. So here we have x squared divided by 4 dx, and then on the y direction we have x squared divided by 2 dx. So in the end we have a b x squared divided by 4 dx plus x2 squared divided by 2, and they both multiply dx. So these two things give us 3/4 x squared. So this integral gives us 1/4 of x cubed from 0 to 2, because from a to b on x, x experience from 0 to 2. So here we have 0 to 2, and then here we get this one equals to 2 as well. So both the fundamental theorem of gradient and also the calculation of the gradient give us the same answer. Now we can apply this fundamental theorem to divergence. So I have fundamental theorem for, guess what? Divergence. It's also often called Gauss theorem. So how does this look like? We have the volume integral. Volume integral of divergence equals to the closed surface integral on the vector itself. So here, the infinitesimal volume equals to dx, dy, dz. And the infinitesimal part, the area, it depends. So how to calculate this depends on what plane you do the surface integral. So for example, if I have x, y, z, so if you are going to do surface integral on the yz plane, then dA equals to dx dy, and the direction is perpendicular to the surface. If you are going to do the surface integral on the yz plane, then dA equals to dy dz. Direction is perpendicular to the surface. Look at an example for fundamental theorem for divergence. So this is example 1.10 of the textbook. So now we have a cubic. The vector is given by this equation. So I have x direction, y direction, z direction. So the question is, what is the volume integral of this divergence? So the first step is to calculate the divergence, which is dvx dx, dvy dy, and then dvz dz. So vx is y squared, so dvx dx give us 0, and then dvy dy give us 2x, and then dvz dz give us 2y. So this is a divergence. So now we are ready to calculate the volume integral. So of the divergence d top. So for x, y, and z, we integrate them from 0 to 1, right? And then this is a divergence. So we have 2x, 2y. and then we have dx, dy, dz. So let's solve this in 3 steps. The first step is this integral. It gives us x squared then 2xy. X equals 0 to x equals 1. So this gives us 1 plus 2y. And the second step, we do integral on this for dy. So this would give us y plus y squared. So y is from 0 to 1. So now we have 2. So the third step is we do integral of this for dz. So what we get is 2z. Z is from 0 to 1. So this equals to 2. So this is the answer. So you can also follow the textbook and do 6 surface integrals and then confirm fundamental theorem for divergence. Last one is fundamental theorem for curl. This is also often known as Stokes theorem. So this theorem is like this. So we have the surface integral of the curl equals to the closed path integral on the vector itself. So if I have a closed path, the surface could be flat, it could be sphere, whatever the shape. The path here would be the boundary that form a closed path. And this is a closed path integral, closed line integral. So we have 2 properties from this theorem. The first one is obviously based on this theorem, the surface integral become independent of shape. So the surface can be flat, or it can be like a sphere above the plane. As long as the boundary form the same closed path, then the integral will give surface integral will give you the same value. The second thing is if we do a closed surface integral on curl, what do we get? We'll get 0. So if the surface is closed, then the boundary would reduce to 0. So here we would have 0. Okay. Let's look at an example for fundamental theorem for curl. So we have this square surface, and the vector is given by this. We have y direction and z direction. So the area is on yz plane for this unit square surface. So the question is, what is the surface integral of the curl? So the first step is to calculate the curl. So I have the determinant where we have x direction dx, and on x direction vx equals to 0, right? And then we have y direction dy, and then on the y direction we have this whole thing, which is 2xz plus 3y squared. And then we have z direction dz, and then we have this term, which is 4yz square. So this one gives us for the x direction. So this term here gives us 4z square, and then this term here gives us 2x. So that's for the x direction, 4z square, and this gives us 2x. And then for the y direction, so this one is not a function of x. This would give us 0. And then this 2 is 0. So nothing on the y direction. And then z direction, we have something. So on the z direction, here we have 2z. And then here we have 0. So this is 2z. So this is a curl. And then for the infinitesimal patch, it's on YZ plane. So this equals to dy dz. The direction is perpendicular to the plane. So we can have the direction is x. And on YZ plane, the variable x would equal to 0. Okay, so now we are ready to calculate the surface integral. The surface integral of the curl. So this equals to this vector dot this vector. So there will only be x direction because nothing on the z direction for dA. And then we have x equals to 0. So this term is 0. So we are only left with 4z square. So I have 0 to 1, 0 to 1, 4z square dz dy. Okay, so let's do this integral first. This would give us 4 divided by 3 z cubed. Z equals 0 to z equals to 1. So this gives us 4 divided by 3. And then we do the second integral for dz. What we get is 4 divided by 3 y. Y equals 0, y equals 1. So this gives us 4 divided by 3. That is the answer to this question. So alternatively, you can also do the line integral over this path. Please follow example 1.11 to finish this line integral and confirm fundamental theorem for curl. I hope you are not overwhelmed by all the examples I showed you earlier. So I recorded this before lectures. I don't think I will go through the examples during live lecture. So the thing is, the 3 examples we practiced before, they are mathematics. They are confirmation of the fundamental theorems. They don't necessarily have physical meanings. For the purpose of this module, for my part of teaching, we focus more on physics. So we are going to use this theorem in very different way, very different to the examples I showed you before. So I hope you have an open mind to what I'm about to say just now. So integral calculus, we have 3 very important things, gradient, divergence, and curl. So gradient, fundamental theorem for gradient will have a lot to do with potential. So gradient of potential, this gives us electrical field, for example. and then the field over a path would tell us how much work has been done. So this would has a lot to do with potential and work. And then divergence would have a lot to do with electrical field, because suppose everything's not moving, everything's static, so electrostatic, the electrical field have divergence. It's a vector spread out. So we will also have Gauss law, which would tell us the value on the for the term on the left hand side. So suppose on the left hand side we have a constant. We know this, and then here we don't actually need to. There are conditions that that will enable us not to do integral at all. So suppose the electrical field doesn't change over a surface, then we can put this electrical field outside of integral. And then this integral is just the total amount of the area, which is a constant. So for that condition, we say we do integral over Gaussian surface. So on the Gaussian surface, our assumption is that the electrical field doesn't change everywhere on the surface. Then we can put the electrical field outside of the integral. And then the integral of the surface is just the total area, it's a constant. So depends on how we use it, we don't actually need to do integral at all. The integral just helps us to link everything together. And then fundamental theorem for curl has a lot to do with magnetic field. So suppose we have steady current, so magnetostatic. So magnetic field would have a curl. So for when we actually use this theorem, we have Ampere law, which would tell us the value on the left hand side. So we don't actually need to do this integral. And then on the right hand side, suppose the magnetic field, it doesn't change over a closed path. Then we can move the magnetic field outside of the integral. Then the closed line integral over a path is just the total length. So we call this line integral over Ampere loop. So when we say there is Ampere loop or Gaussian surface, we say the field is constant everywhere on the surface or on the loop. We call this symmetry. So when there is property of symmetry, we can move the field outside of the integral. And then the integral here, what's left in the integral is just a constant. It's a total area here, it's a total length here. So we're going to learn them one by one over and over again. We're going to do a lot of practice and I hope it will make sense. But the important thing to remember is that all of these, they are similar to the four concepts for differential calculus. We have del operator, we have gradient, divergence, and curl. And then for integral calculus, it can be very complex. The mathematics can be very complex. But in terms of concept, we also only have four concepts, which is fundamental theorem of calculus, and then we apply this to gradient, divergence, and curl. So try to simplify this, and then to a degree that you can use it for physics, that would be enough.